Now, this is an example of a cantilever slab, and where in general, where we will get a cantilever slab, the sunshade. Example of a cantilever slab is sunshade. What do you mean by sunshade? On every opening, that means door or window. Doors అయితే outside ఉన్నవి, windows outside ఉన్న windows కి బయట నుంచి వచ్చే రెయిన్ వాటర్ లోపలికి రాకుండా ఆర్ సన్ రేస్ ని రెస్ట్రిక్ట్ చేయడం కోసం మనం టాప్ ఆఫ్ ది ఓపెనింగ్ పైన బయటకి ప్రొజెక్ట్ చేస్తూ ఒక స్ట్రక్చర్ కడతాం. దట్ ఈస్ కాల్డ్ సన్షేడ్. Okay, exactly over the opening we will get a lintel. From that lintel sunshade will be projected outwards. Okay, as that sunshade is fixed to the lintel and free at the other end, it is one of the example of a cantilever slab. Okay, another example, if you have a balcony projecting from a building. Everybody know what you mean by a balcony. Balcony is not a room space which is inside your building lopala unte dani balcony anam kada. Outside the building ki project ayi undal, baitak project ayi undal, then it is called as a balcony, right? So that balcony that balcony slab is also one of the example of a cantilever slab. Okay, now let us discuss in detail the coming to structural behavior of a cantilever slab. We know that a simply supported slab will be subjected to sagging moment, right? A simply supported slab will be subjected to sagging moment. What do you mean by that? You will get compressive stresses at the top, you will get tensile stresses at the bottom. That's why we will provide a tension steel at the bottom of the slab instead of at the top of the slab. మనం స్లాబ్లో బాటంలో స్టీల్ పెడతాం కానీ టాప్లో స్టీల్ పెట్టాం. If you consider the thickness of a slab like this, we'll provide the steel at the bottom. Why we are not providing at the top? Because in a sagging moment slab, that means in case of simply supported which is subjected to sagging moment, you will get tensile forces at the bottom, tensile stresses at the bottom. That's why steel is provided at the bottom. Okay, but in case of cantilever slabs, the type of moment what we will get is a hogging moment. In case of hogging moment, the tensile stresses will be developed at the top and compressive stresses will be developed at the bottom. That means positive compression at the bottom, negative stands for tension at the top. Okay, this is the condition for a cantilever slab. So where we have to provide tension steel in case of a cantilever? At the top itself. Why? Because it is subjected to tensile forces or tensile stresses. If you see this diagram, okay, if you see this diagram, this is the slab outer part. Okay, this is the slab portion, and in between that there is a line, right? Here I have represented that with main bar. So that is main steel which resists bending. Main steel which resists bending. Okay, and instead of providing that bar, if you provide at the bottom, it will fail. Why? Because at the bottom compression is there steel is not required. We need steel in the tension zone. And wherever the bars we can see like a dot here, all these dots are called as distribution bars. Asal distribution bars ane term enduku vastundi? Before that, once recall what do you mean by a one way slab. మా ఇప్పుడు ఈ ప్రాబ్లము మీకు మెటీరియల్ 2-way స్లాబ్లో ఇచ్చాను. ఓకే, బట్ ఇట్ ఈస్ నాట్ ఎ 2-way స్లాబ్. Once recall what do you mean by one-way slab. We have two conditions for a one-way slab. One is whenever a slab is supported on only one edge or it is supported on only two opposite edges, then it is called one-way slab. Let me explain here. Already these details are clearly explained. So this is a slab where only this edge and this edge, these two opposite edges are supported by walls or column or something. It is supported. This edge and this edge both are supported. These two long edges are unsupported. Then it is called a one-way slab itself, right? Why? Because as the load distribution will happen only along one direction, as it is supported along only one direction, it is called as one-way slab. And whenever another case, second case enti, whenever a slab is supported by all the four edges, Let us assume this slab is supported by all the four edges. Anni edges lonu slab support ayyundi, and if Ly by Lx ratio, that means longer span to shorter span ratio, if the ratio of Ly by Lx is greater than 2, okay, if that ratio is greater than 2, then it is also called as one way slab. These are the two conditions for one way slab. ఇప్పుడు ఒకసారి ఇది చూడండి, coming to this particular cantilever, out of four edges of a cantilever slab, how many edges will be supported? I will draw a plan here. Let us assume this is the plan of the slab, and this is the edge where it is fixed, okay, and this is the edge where it is completely free. That means these two are also free. As this edge, as this edge is only one of the edges supported and the remaining three are unsupported, so this is called as a cantilever slab, right? Now, as this is one edge is supported, this will be called as one way slab itself, okay. Mari two way slab ante, if all the edges are supported and the ratio of longer span to shorter span is less than or equal to 2. First of all, longer span to shorter span ratio eppudu check cheyali? Only when all the edges are supported. Anni edges support untene appudu check cheyali. If any one of the edges is unsupported, without any checking, you can clearly say it as a one way slab, okay. Now, as cantilever is supported on only one edge, it is called one way slab. Now, in case of one way slab, we know that along one span we will get main steel, along another direction we will get distribution steel. As a cantilever is bending along this way, this will be a main steel, the line which you can see as a line, that is main steel, and the dots are represented as distribution steel, okay. Now, coming to the main important discussion in this, if you understand this carefully, the cantilever slab at the fixed support is somewhat higher than at the free end. If you observe carefully, these two are not same. In the diagram itself, if you observe carefully, this is higher and this is lower. Why the thickness of a cantilever slab is reduced towards free end? Because the bending moment at the fixed end is very, very high, and the bending moment at the free end is zero, simply zero. It is not even less, it is simply zero, right? And we know that the thickness of the slab and the reinforcement in the slab. Remember, the thickness or depth, we can call it as depth of the slab. The depth of the slab or and AST of the slab, that means area of steel required in the slab. These two are completely depends on bending moment. If bending moment is very high, then area of steel is requirement is higher and depth of the slab requirement is also higher. Whenever you have less moment, then the thickness of slab as well as area of steel requirement is also less. That's why to maintain this slab as economical design, what we are doing is we are providing somewhat more depth, whatever the depth we will assume at the starting, that we will provide at the fixed end, and towards the free end we will reduce that depth, and reduce చేసి ఎంత పెడతామంటే it should not be less than 75 mm. Okay, for example, if the design says that only 20 mm is more than sufficient at the free end, but the code is saying that you cannot provide a depth at the free end less than 75 mm. Okay, 75 కంటే తక్కువ ఏదో ఒక వాల్యూ ప్రొవైడ్ చేయొచ్చు, అండ్ దట్ ఈస్ ఆల్సో సబ్జెక్టెడ్ టు చెక్ ఫర్ డిఫ్లెక్షన్, అది చెక్ చేసి ప్రొవైడ్ చేయాలి. Okay, that we will see in the design. And coming to the AST, we know that the moment, bending moment in a cantilever condition will be higher at the fixed end and lower at the free end. Free end దగ్గర తక్కువ ఉంటుంది, fixed end దగ్గర ఎక్కువ ఉంటుంది. That's why the main steel, whatever the main steel we will get after design, that will provide only up to certain length. కొంత లెంత్ వరకే పెడతాం అండ్ తర్వాత రిమైనింగ్ దాంట్లో సగం కట్ చేసేసి కంప్లీట్గా ఇంకా రిమైనింగ్ బార్స్ లాస్ట్ వరకు పెడతాం. ఫర్ ఎగ్జాంపుల్ ఇక్కడ మనకి 10 బార్స్ వచ్చాయనుకోండి. The design says that provide 10 bars of some 8 mm diameter. That is the design. Okay. But దీని తర్వాత at certain length తర్వాత ఏమవుతుందంటే మూమెంట్ తక్కువ ఉంటుంది కదా, అక్కడ 10 bars అవసరం లేదు. What I will do is provide 0.5% of AST అంటే 5 bars పెడతాను. That is more than sufficient. Why? Because the moment is less, that 5 bars is more than sufficient. ఇంకా remaining bars 5 కట్ చేసాం కాబట్టి that will reduce the cost of construction. Okay, but a certain length enta, at what distance you have to cut that bars, that length is 0.5 times of L, where L is span, that means half of this span, or LD. LD is a new term what we are studying now, which is called as development length. Okay, I will explain in detail. LD stands for development length, right? Now let us once discuss. సో ఇక్కడ ఏంటంటే ఈ రెండు వాల్యూస్ చూడాలి, ఈ రెండుట్లో ఏదైతే హయ్యర్ వస్తుందో అంత పెట్టాలి ఇక్కడ. ఓకే, అట్ దట్ ప్లేస్ యూ కెన్ కట్ ద బార్స్ ఫర్ ఎకనామికల్ డిజైన్. అండ్ లెట్ మీ ఎక్స్ప్లెయిన్ వాట్ యూ మీన్ బై ద డెవలప్మెంట్ లెంత్. అండ్ లెట్ us assume there is a slab.
క్లాస్ జరుగుతుంది.
ఎవరు మా మాట్లాడతాను. Let us assume this is the slab and here we are hanging some 50 kgs of weight. Okay, I'm hanging 50 kgs of weight to a hook. Okay, there is a hook here. For this hook I am hanging a weight of 50 kg. Now what happened is, so see here, before construction of this slab, this bar of the hook is embedded into the concrete. And a slab lopalki certain length is embedded. Okay. Now let us assume this length is x mm. Everybody know this. ఇప్పుడు మనం సీలింగ్ ఫ్యాన్స్ ఒక హుక్ కి హ్యాంగ్ చేసాం. ఆ హుక్ ఎక్కడి నుంచి వచ్చింది? కన్స్ట్రక్షన్ అంతా అయిపోయిన తర్వాత మేకులతో కొడతారా? కాదు. Before construction itself, that hook will be placed in that position. ఆ పొజిషన్లో అది ప్లేస్ చేసేసి తర్వాత కాంక్రీటింగ్ చేస్తాం. లైక్ అట్లే ఇక్కడ కూడా ఈ హుక్ని ఇక్కడ ప్లేస్ చేసేసి తర్వాత కాంక్రీటింగ్ చేస్తాం. సో దట్ దట్ కాంక్రీట్ విల్ బైండ్, క్రియేట్ ఎ బాండ్ బిట్వీన్ దిస్ బార్, hook bar and the surrounding concrete, so that this hook will be stable and will lift this entire weight. Okay, that's the main concept behind it. Now let us assume there is a weight of 50 kg hanging on this particular hook. Exactly after application of this load on the hook, previously there is no load, the hook is just simply embedded in the concrete with a length of x mm. Now after everything is over, that means after construction is over and everything is fine, we have added this 50 kgs load to this hook. Exactly after application of this load, this hook is completely failed and bite వచ్చేసింది. It is completely failed and it removed and it has completely come out of this slab నుంచి బయట వచ్చేసింది. What is the reason behind it? And let me tell you one more case. There is one more hook at the side. Okay, same type of hook, no change in that, same type of hook with the same material. This material, whatever the hook made up of, which is, let us assume this is steel of some 8 mm diameter. 8 mm diameter steel hook idi kuda 8 mm diameter steel hook, same. And this time the embedded of this hook is y mm. By means of this figure you can clearly understand x mm is somewhat less than y, x is less than y. The depth of embedment is more in this second case. Now after completion of construction of slab and everything is over, I have added the same 50 kgs of weight on the second hook. Okay, now it is not failed. It is bearing that 50 kgs. Can you tell me what is the reason behind these two? Why X is failed and why Y is not failed? Both are made up of X and Y materials are made up of same material with the same diameter. Why first hook is failed after application of 50 kg load? Why the second hook is not failed under application of same 50 kg force? Can anybody tell me the reason? Bond strength increases. Actually, which material is resisting this 50 kgs of load? Concrete? No. Is the hook resisting 50 kgs? No. The bond between the concrete and hook. ఓకే ఇప్పుడు మనం యాడ్ చేసిన 50 కేజెస్ ఈ హుక్ కాదు మా బేర్ చేస్తాను నేను అట్లా అని చెప్పి పైన ఉన్న కాంక్రీట్ బేర్ చేస్తాను అంటే కాంక్రీట్ కూడా కాదు. ఇట్ ఈస్ ద యాక్షన్ బిట్వీన్ బోత్, అంటే ద బాండ్ బిట్వీన్ ద కాంక్రీట్ అండ్ ద స్టీల్ సర్ఫేస్. మనం ఎంబెడ్ చేసిన స్టీల్ సర్ఫేస్కి చుట్టూ కాంక్రీట్ ఉంది, ఆ రెండింటి మధ్యలో ఉన్న అడేషన్. You know what you mean by cohesion and adhesion. So the adhesion between the steel embedment and the surrounding concrete is resisting 50 kgs. It's not hook and not concrete. Okay, and as this adhesion area is very less in first case, it is failing. But in the second case, as the surface area of the steel with concrete is increased, the adhesive force, that means the bond force, will increase. That's why it is safe against 50 kgs of applied force. Okay, so here whatever the length you have provided, whatever the depth of embedment you have provided in the concrete to resist the applied force, that length is called development length. Remember this carefully. Development length means the depth of or the length of embedment of the steel bar into the support, that may be a slab or beam or anything. The embedment of the steel bar into the support to resist the application of load is called development length. Okay, this is the formula. And to calculate LD, that we will discuss later. There is a formula for calculating LD that is there in the code also, that we will discuss later. Now the condition is, here it is a cantilever slab, right? This is a cantilever slab and this straight bar is provided to resist the tension, and up to the face of the support this bar is important to taking of tensile stresses. Now what will happen if you exactly cut this bar at this portion? If you cut the steel bar exactly at the face of the support, you are not providing this bar into the support local work pettatledu, only support work betti cut chestunam. Emaitadi, this surface will completely cut off and this concrete slab will fall down. అట్లా కాకుండా ఉండాలంటే ఏం చేయాలి? This bar will be embedded into the support to a length of LD. Here I have mentioned, from the face of the support to the length it is embedded into the support, that is called development length. ఇక్కడ ఎందుకు సార్ మళ్ళీ కర్వ్ చేసి మళ్ళీ తీసుకొచ్చి స్లాబ్లోకి పెట్టారు అంటే, ఫర్ ఎగ్జాంపుల్, ఇఫ్ ద విడ్త్ ఆఫ్ ది సపోర్ట్ ఈస్ 300 mm, let us assume the width of the support is 300 mm and development length required is just 200 mm. Just assume the development length required is 200 mm. అప్పుడు ఏమవుతుంది, ఫేస్ ఆఫ్ ది సపోర్ట్ నుంచి ఒక 200 mm పెడితే లెంత్ సరిపోతుంది. అంటే లాస్ట్లో ఒక 100 mm వదిలేయచ్చు మనం. నో నీడ్ ఆఫ్ దిస్ బెండింగ్ ఆల్సో. Just from the face of the support, if you provide for a length of 200 mm, that is sufficient. Okay, that is more than sufficient. But whenever you have a development length of some 500 mm, 500 mm ఇలా పాసిబుల్ ఉందా మనకి? ఇటు ఉండేది 300. అప్పుడు ఏం చేయాలి, ఇటు సైడ్ ఒక 250 తీసుకొచ్చి మళ్ళీ కిందకు ఒక 250 పెట్టాలి. బెండ్ చేస్తే యూ విల్ గెట్ దట్ లెంత్ అవైలబుల్. అండ్ ఇఫ్ యూ గాట్ 500 mm, నాట్ 500, 700 mm, అప్పుడు ఏం చేయాలి, ఇటు తీసుకొచ్చి కిందకి తెచ్చి మళ్ళీ ఇంకొక బెండ్ చేసి మళ్ళీ స్లాబ్లోకి తీసుకుపోతే యూ విల్ గెట్ దట్ లెంత్. Okay, that is what bending here I have shown. It all depends on LD value. Okay, now let us go to the design procedure of a cantilever slab. And I'm just recalling one point. If you want to design a cantilever slab, it already over. Simply saying it already over. Why? Because we have already studied one-way slab design. One-way slab design, cantilever slab design, both are same. There is no change at all, but only one step will be added. ఒకే ఒక్క స్టెప్ యాడ్ అవుతుంది. ఇక్కడ ఎల్డి అనే టర్మ్ ఉంది కదా, ఆ ఎల్డి అనే టర్మ్ ఫైండ్ అవుట్ చేయాలి. వీ హ్యావ్ టు ఫైండ్ ద వాల్యూ ఆఫ్ ఎల్డి రిక్వైర్డ్. అదొక్కటి యాడ్ అవుతుంది. అండ్ ఇన్ అడిషన్ టు దట్ వన్ మోర్ అడిషన్ ఈస్ this one slab bending moment formulas. In case of simply supported case, for bending moment we have used a formula called WL square by 8, and for shear force we have used a formula called WL by 2. These are the formulas for simply supported condition loaded with UDL. Now what is the condition here? The cantilever slab loaded with UDL. It's not simply supported. Now tell me formula for M and formula for shear. Tell me the formula for bending moment and formula for shear for a cantilever beam loaded with UDL on entire span, and into pi divided by 4 times of tau BD. This is the formula for calculating development length. ఈ ఫార్ములా నేను ఇప్పుడు ఇక్కడ ప్రాబ్లంలో యూజ్ చేసి ఉంటాను. ఆ ఫార్ములా ఎక్కడి నుంచి వచ్చిందంటే దట్ ఈస్ టేకెన్ ఫ్రమ్ క్లాస్ నెంబర్ 26.2.1. In that we have one more value called tau BD in the denominator. Formula ఇందాక చెప్పాను, పై అంటే diameter and tau is sigma s is 0.87 times of Fy. Fy అంటే grade of steel given in the question. And in the denominator there is a value called tau BD, which you mean by design bond stress. మన compressive stress, tensile stress ఎట్లయితే ఉంటుందో, there is a bond strength between the bar and the surrounding concrete. So it all depends on the surface area. So a bond stress ఎంత ఉంటుందంటే that is taken from class number 26.2.1.1. Let us see that one. Here there is a table in the next page itself. Page number 43. Design bond stress in limit state of method for, see here, this is very very important. ఇక్కడ ఇచ్చిన tau BD values ఏ టైప్ ఆఫ్ స్టీల్కి, ప్లెయిన్ బార్స్కి, అంటే ఎంఎస్ స్టీల్ FE 250 గ్రేడ్ ఉంది కదా దానికి మాత్రమేమో. దీస్ వాల్యూస్ ఆర్ నాట్ ఫర్ HYSD బార్స్, అంటే FE 415కి FE 500కి కాదు. దీస్ వాల్యూస్ ఆర్ ఓన్లీ ఫర్ MS బార్స్ విచ్ ఈస్ FE 250 గ్రేడ్. అండ్ ఇంకొకటి, this is taken for compression tension zone only. If the hook is in tension zone, then only these values will be helpful. So ఈ values ఎప్పుడు తీసుకోవాలి? If it is MS steel and that is placed in tension reinforced, or that is placed in tension zone, then only these values will be considered for tau BD. ఒకవేళ HYSD bars అయితే ఏం చేయాలి? See here, for deformed bars conforming to this grade, this is the code of practice for HYSD bars. Okay, these values shall be increased by 60%. ఓకే, 60% అన్నారు. ఒకవేళ మనం యూజ్ చేసిన బార్స్ HYSD బార్స్ అయితే ఇక్కడ ఇచ్చిన వాల్యూ tau BDకి ఒక 60% ఇంక్రీజ్ చేయమని చెప్తున్నారు. అంటే దాని మీనింగ్ ఏంటంటే ఇందాక మీకు చెప్పిన LD ఫార్ములాలో 4 times of tau BD అని ఉంది కదా. ఇప్పుడు మనం M20 గ్రేడ్ కాంక్రీట్ వాడుతున్నాం అనుకోండి. ఫర్ ఎగ్జాంపుల్, ఇఫ్ యు ఆర్ యూజింగ్ M20 గ్రేడ్ కాంక్రీట్, tau BD వాల్యూ ఈజ్ 1.2. ఓకే, బట్ యాజ్ ఇట్ ఈస్ మనం ప్రాబ్లంలో చేసింది FE 415 గ్రేడ్ స్టీల్ కదా, ఇట్స్ నాట్ FE 250. అప్పుడు ఈ వాల్యూ డైరెక్ట్గా తీసుకోకూడదు. ఎంత ఇంక్రీజ్ చేయాలి? 1.6. దట్ మీన్స్ 60% ఇంక్రీజ్ చేయాలి. జస్ట్ మల్టిప్లై విత్ 1.6. నౌ దిస్ ఈస్ ద వాల్యూ ఆఫ్ tau BD ఫర్ M20 grade concrete and HYSD bars. Okay, not 1.2. 1.2 multiplied by 1.6. Next, ఒకవేళ మనం ప్రొవైడ్ చేసిన హుక్ కంప్రెషన్ జోన్లో ఉందనుకోండి. ఓకే, ఫర్ బార్స్ ఇన్ కంప్రెషన్ ద వాల్యూస్ ఆఫ్ బాండ్ స్ట్రెస్ ఫర్ బార్స్ ఇన్ టెన్షన్ షల్ బి ఇంక్రీజ్డ్ బై 25%. అంటే ఫర్ ఎగ్జాంపుల్ ఇప్పుడు మనం చేస్తున్న దాంట్లో ఎస్ లెట్ us explain this category. There is a cantilever slab. ఇది cantilever slab అండి. నేను క్యాంటిలివర్ స్లాబ్ బాల్కనీలో ఒక ఫ్యాన్ హ్యాంగ్ చేసుకోవడం కోసం ఒక హుక్ పెట్టాను. ఓకే, ఈ హుక్ మనం బాటంలోనే కదా పెడతాం. A cantilever slab will be subjected to compressive stresses at the bottom, not tension. ఇప్పుడు ఈ హుక్ కి బాండ్ స్ట్రెస్ ఫైండ్ అవుట్ చేయాలి. This hook is made up of HYSD bar. It's not yield, it's not MS bar. ఇప్పుడు tau BD value ఎంత? For M20 grade concrete, it is 1.2 as it is. As it is made up of HYSD bar, it is increased by 60%. And this hook is provided in compression zone. That's why it is again multiplied by 1.25. ఈ 1.25 ఏంటంటే కంప్రెషన్ జోన్లో ఉంది కాబట్టి ఇంక్రీజ్ చేసాం. అండ్ దిస్ 1.6 is as the hook is made up of HYSD bar, I have increased. And this 1.2 is your bond value. Okay, this is the condition. And that we'll discuss in detail in the problem. And coming to basic values, see here, the basic values for cantilever it is 7, for simply supported it is 20. Already this we have done many times. Now for this case, for cantilever we have to consider 7. Okay, now coming to the step by step procedure, I will go with a fast explanation. Why? Because everything is same. Coming to the question, it is a cantilever slab projecting 1.5 meters from a beam. Beam నుంచి బయటకి 1.5 meters project అయింది. And M20 grade concrete, Fe 4 and 5 steel are used. Live load on the slab is 2 kilonewton per meter square. Floor finish is 1 kilonewton per meter square or acting on the slab. This is the detail given. And you just write all the given details first. Later on, the first assumption is thickness of slab. And we have studied that the range for simply supported slab, what we have taken is L by 25 to L by 30, right? We have taken L by 28 for many problems. This range for cantilever is L by 10, span by 10. You just remember this. While assuming the depth of this slab for a cantilever, it will be span by 10. And span given is 1500. So that's why we got effective depth of 150 mm. And overall depth, I have assumed 25 mm as effective cover. That's why 175 mm will become overall depth. Okay. Now coming to next step, loads per meter length. Just a minute. Srinivas, take attendance. So the next step is loads per meter width of slab. This is same, process is same. Write down the live load, write down the floor finish. And one important step here, self weight of this slab. How you have determined self weight of this slab in the previous cases? Overall depth multiplied by the unit weight of concrete. That is what the formula for calculation of self weight per meter square. Okay, but here what I have made an assumption is, as this 175 mm depth is not provided throughout the length, slab మొత్తం starting fixed end నుంచి free end వరకు same thickness provide చేయట్లేదు. For reducing the cost of construction, for reducing the material, what I am doing is, this depth may be gradually reduced to 100 mm. అంటే ఈ లాస్ట్లో వచ్చి 175 ఉంటుంది, టాప్ హార్జాంటల్గా ఉంటుంది, ఎందుకంటే మనం నడవాలి కదా, పైన ఇంక్లైన్డ్ పెడితే కుదరదు. బట్ కింద వచ్చేసి ఇంక్లైన్డ్గా ఉంటుంది స్లాబ్. అండ్ అట్ ద ఎండ్ చూసేసరికి ఇక్కడ 100 ఉంటుంది. ఓకే, హియర్ ఇట్ ఈస్ 175 అండ్ అట్ ద ఫ్రీ ఎండ్ ఇట్ ఈస్ 100. ఇప్పుడు సెల్ఫ్ వెయిట్ ఆఫ్ ది స్లాబ్ అంటే ఏది కనుక్కోవాలి? యూ షుడ్ నాట్ యూజ్ 175. వై? బికాస్ ఇట్ ఈస్ నాట్ త్రూ అవుట్. యూ షుడ్ నాట్ యూజ్ 100. ఇట్ ఈస్ ఆల్సో నాట్ త్రూ అవుట్. యూ జస్ట్ టేక్ యావరేజ్ ఆఫ్ దీస్ టూ. Okay, average thickness of these two. So 0.175 plus 0.1 by 2 will get average thickness multiplied by unit weight. You will get the self weight of slab. Now the total working load is 6.44 kilonewton per meter square, and the factored load will be multiplied by 1.5, which is 9.66 kilonewton per meter square. Okay, next step is calculation of bending moments and shear forces. I have already said many times, as the slabs are very safe in shear, no need to calculate shear force, or if you want to calculate, no problem, you can do it. So the formula for bending moment is WL square by 2, which is equal to 9.66 multiplied by 1.57 square by 2. See here, one important thing, the slab span given is 1500. Here we have used a value of 1.57. 1.5 kada answer. 1.57 ఎందుకు యూజ్ చేసాం? భాస్కర్ 130. Mute your audio. So here instead of 1.5, why we have used 1.57? Here see, second step, we have forget about this one. Effective span. For a cantilever, you just remember the condition. For a cantilever slab, the effective span is centered of the support to the end of the slab. This is one case. Another case is the clear span plus d by 2. మనం సింప్లీ సపోర్టెడ్కి అయితే క్లియర్ స్పాన్ ప్లస్ డి యాడ్ చేస్తాం, క్యాంటిలివర్కి బై 2. దిస్ ఈజ్ ఆల్రెడీ ఎక్స్ప్లెయిన్డ్ ఇన్ ద జనరల్ డిజైన్ రిక్వైర్మెంట్స్ ఆఫ్ బీమ్స్. ఓకే, యూ జస్ట్ ట్రై టు recollect the information from there. So the effective span will be clear span plus d by 2. D in this step we have determined, right? So which is 1.575. This value I have substituted here. Okay, so total moment is 11.9 kilonewton meter, and I'm checking the depth whether it is safe or unsafe. So the formula is same what we have used for simply supported one-way slab, two-way slab, and beams, everything annitki same formula. So mu by kfckbd, where we got 65 mm. See here, based on bending check requirement, the depth of slab required is just 65, but how much we have provided? 150. Hence it is very safe. You cannot compare this value with end value. అంటే 100 పెట్టాం కదా, దాంతో కంపేర్ చేయొద్దన్నమా. ఎందుకంటే ఇక్కడ మనం యూజ్ చేసిన బెండింగ్ మూమెంట్, మాక్సిమం బెండింగ్ మూమెంట్ ఎక్కడ వస్తుంది? ఫ్రీ ఎండ్లోనా, ఫిక్స్డ్ ఎండ్లోనా? This bending moment 11.9. This is the maximum bending moment at the fixed end, not at the free end. That's why whatever the depth we have provided here, that we have to check. Okay. Now, as it is safe against bending, we can write this statement: provided depth is adequate. Now, the last step, not last, tension steel calculation. The formula is same: bending moment equal to T into Z. T into Z formula, and here only AST is unknown. And after substitution of all the values, we got AST as 226. And you know that this value is only based on design, but as per code, minimum steel we have to check whether it is within the limit or not. So based on this minimum calculation, we got a minimum steel of 210 mm square. Okay, 210 mm square, but what we got is more than minimum. That's why the AST is finalized as 226.85 mm square. Okay, now for calculation of spacing, I assumed 8 mm diameter. So pi by 4, 8 square divided by the total AST. Now here we got a spacing of 221, and that I have assumed as 220. And maximum spacing check 3D and 300. Srinivas, just once unmute your audio.